Hello, this is a walkthrough for the fall 20, no, that's not fall, that's final, that F is final, the spring 2017 final for MA265. We have a bunch of questions to go through, and this is, just to be clear, going over the midterm 2 related material. There's already a video for all of the midterm 1 material. And in the future, there'll be one going over the entire thing. Number 7, let's compute this determinant. We know that if there is a row or a column that only has one element, one non-zero entry, we can pull that entry out with the sign associated with that entry's position, and then take the determinant of what's left and multiply it by whatever that non-zero number was. So looking here, we have a 1 sitting in a row by itself. And we know that this position in the matrix will have the sign plus, minus, plus, minus, plus when we take its cofactor. And so I'm going to pull out a 1 with a positive sign. And I'm not going to write out the whole matrix because it's pretty big, but what we're going to do is cross out the row and the column containing that 1 and look at what we have left. And it may be difficult to see, it's a little weird to kind of try to stitch this back together without writing it back out, but we have a 3 that's by itself in that top row, and that 3 will have a minus sign. So we can multiply things by -3 and find the determinant of the matrix left here. Now we're just left with 9 elements, this 1, 2, 3, a 3, 2, 4, and a 0, 0, 5. We see that that 5 will have the sign plus, minus, plus, minus, plus. And so we can multiply by 5 and cross out the row and the column that that 5 is in. And now we're left with a 2 by 2 determinant, which is 1, 3, 2, 2. This will give us -4 multiplied by that 3 is 12. 12 times 5 is 60. 7 is A. Skipping 8 and 9, consider the vector space P2 of all polynomials of degree at most 2. Find all real numbers such that t squared minus at plus 1 minus a squared is in the span of these other 3 vectors. So let's take these 3 vectors and express them as vectors. Did I say vectors? Let's take these 3 polynomials and express them as vectors. This first one, writing the entries like t squared, t, and then some constant, whatever constant we have there. This first polynomial can be expressed as 1, -2, 1. Our second polynomial is 0, 1, -1. And our third polynomial is 3, -2, -1. And we're trying to find the values of a for which this guy is in the span, so we can just set up an augmented matrix with these 3 and then t squared, so 1 minus at, and then 1 minus a squared here. Let's see, I'm going to duplicate this matrix over so that we have a copy to work with, and let's simplify things down. Let's add 2 row 1s to row 2. That will give us 0 here, plus 6 is 4, plus 2 here. And what should we do now? Let's subtract a row 1 from row 2. That gives us 0, -4, and -a squared. If we flip the sign of all the entries in row 3, we get that, and now we see that if this system is consistent, that implies that this vector, or the vector represented by this polynomial, is in the span that we found here, and this would mean that both of these rows would have to be equal because, because this is not an augmented matrix, we want 1x2 and 4x3 to always be equal to the same thing. So we can set a squared equal to negative a plus 2, or a squared plus a minus 2 is equal to 0. And solving this, we will get a plus 2, a minus 1 is equal to 0, so a is equal to 1 and negative 2. D is our correct answer for number 9. 10. Consider this linear system. Which of the following... Oh, that's not what it says at all. Suppose that the solution set of this system is a linear subspace of R3. Which of the following conditions must hold? So this is actually a much simpler question than it would look like, and you try not to get distracted by the vector that someone thought was a little funny to put there. But what we can do here is just recognize that our four main subspaces that we know about that exist for every matrix is our row space, our column space, our null space, and the null space of A transpose. Additionally, we know that the null space is a subspace of however many columns our matrix has. So in this case, the null space is a subspace of R3. And additionally, the null space is the solution to AX equals 0. So no matter what value of little a we have here, as long as b is equal to 0, this will represent the subspace AX equals 0, the null space where a is 117212004311a. And we know that that is a subspace of R3. So b is equal to 0, that is our condition there. And so 10 is in fact E. Skipping 11, 12, 13, 14, 15, these are all either final questions that we haven't learned yet for at least when I'm taking midterm 2, or they are or they're midterm 1 information. This test is a little weirdly ordered. 16, let V be a member of R2. Oh, that's weird notation. I'm bad at reading this kind of thing. So let V be the set of vectors in R2 composed of x, y, where x times y is greater than or equal to 0. Which of the following statements is true? So let's graph this out. What conditions do we need for x times y to be equal to 0? Well, all of the coordinate axes will work because one or both of our values x and y are equal to 0. Additionally, if x and y are greater than 0, this condition will hold. And if x and y are less than 0, this condition will hold. If we take any vector in this space and multiply it by some constant, it is not going to change whether or not x times y is greater than or equal to 0. But the thing is, let's take this scaled vector right here and add it to a vector on the other side. We are going to get a vector that is no longer in the set. So we are not closed under vector addition, and therefore we're not a subspace. So 16 is C. 17. Let A be an m by n matrix if W is the column space of A transpose, aka the row space. And one important thing to remember about the row space is that the row space is orthogonal to the null space. And again, like most things, I don't actually have a proof for that. That's just a thing that I've read on the internet and solves this question. Then the orthogonal component of W is what? So At this point in the curriculum, whatever date is April 2nd, it's April 2nd, we haven't learned exactly the phrase orthogonal complement, but what we do know is this fact right here, that the row space is orthogonal to the null space, and because the column space of A transpose just is the row space, then it's pretty fair to say that the answer to this will be the null space of A. So 17 is A. 18, let A equal this guy right here. We're looking for the cofactor of A 3, 2. So the 3, 2 position of A is right here, and the cofactor is going to be the sign at that position in the matrix. So that'll be determined by plus, minus, plus, and then 1 over. So minus, we'll have a minus sign there, -1, multiplied by the determinant of the matrix that we get by crossing out the row and the column of 3, 2, so the second column and the third row. We are left with a matrix composed of 1, 2, 0, 3, -4, -1, 0, -1, 0. That it's determinant here, and if it'll switch, there we go. Now we can expand this further by noting that we have a -1 in a row a column all by itself, and so we can see that this -1 has a sign of 1, 2, 3, 4, a sign of -1. So we can expand this, and we'll have -1 multiplied by -1 multiplied by -1, because we have to pull this -1 out, and we have a determinant here, 1, -1, 0, 3, and that determinant is just another -1. So this is a little bit silly how it ends up looking, but our answer is 1. D for problem 18. 19. Let P4 be the space of all polynomials of degree at most 4. The subspace V of P4 consists of all polynomials P of t such that P of 0 is equal to 2P of 1. What is the dimension of V? So if we have a general polynomial that's a member of P4, P of t, that'll take the form A0, where A is constant, plus A1t plus A2t squared plus A3t cubed plus A4t to the fourth. We'll see that P of 0 in all cases will be A0, and that 2 times P of 1 will be 2A0 plus 2A1t plus 2A2t squared plus 2A3t cubed plus, oh, sorry, I'm not plugging in the 1s, all right. Yeah, so all these t's are 1, plus 2A3 plus 2A4. Now, if we take a closer look here, we see that the relation that they give us is saying that A0 is equal to, among other things, 2A0. And the only way for this to be true is if A0 is equal to 0. So we can express our polynomial P of t over here as 0 plus A of t plus, A1t plus A2t squared plus A3t cubed plus A4t to the fourth. And therefore, since we only have 4 variables that we can mess with to control how our polynomial looks, we have 4 degrees of freedom. The dimension of the subspace V is 4. So 19 is in fact C. Question 20. Let A be that matrix given there. Find all the values for C for which the system AX equals 0 has a non-trivial solution. So if AX equals 0 has a non-trivial solution, by the invertible matrix theorem, we know a bunch of other things about this matrix. We know, for one, that it doesn't have, it has fewer than n pivots. because what AX equals 0 also implies is that the matrix is non-invertible, and therefore that the determinant of this matrix must be 0. And just to add another fact in there, AX equals 0 having non-trivial solutions means that the null space of A is not 0-dimensional, that there are some values that after the transformation takes place, there are some values that are all squished onto the origin. So I'm just going to take the tact of solving the determinant to find the values of C for which the determinant is equal to 0. And solving for that, just using the cofactor expansion, I think that's what they call it, we'll have 1 multiplied by the determinant C negative 3 2C minus 1 times negative 1, so plus 1 times 1, 1, 2C plus 2 times 1, 1C negative 3. And all this is equal to 0. I can get rid of these 1s. This is C squared plus 6. C squared plus 6. This is C minus 2. C minus 2. And this will be 2 times negative 3 minus C. Oh, sorry, I hope that wasn't too loud. I obviously need to turn my notifications off. So we see that 0 is equal to C squared. And where are our C's? We have plus 1C minus 2C, so minus C, plus 6 minus 2 will give us 4, minus 6 will give us negative 2. This factors to C minus 2, C plus 1, or C equals 2, 2 and negative 1. So 20, our answer is in fact E. 21, find a non-singular matrix P such that this whole thing holds. Let's rearrange this a little bit and we'll get a diagonalization expression that we're more familiar with. Let's multiply the left side by P and the right side by P inverse, and we will get 2, negative 2, 2, negative 2, 1, negative 1, 3, negative 1, 2, negative 4, 3 is equal to P 1, 0, 0, 0, 1, 0, 0, 0, 6 P inverse. So what this is telling us is that 1, there is some matrix P such that this relation is true, implying that this matrix over here, we'll call it A, just to be simple about it. We know that A, as a result of this, is diagonalizable. And since A is diagonalizable, we know that this diagonal matrix D encodes the eigenvalues of A. So lambda 1 is equal to 1, lambda 2 is equal to 6, and there's a multiplicity of 2 here. And then we also know that P will be composed of the eigenvectors associated with these eigenvalues. So let's solve using lambda 1 equals 1 for the eigenvectors. So subtracting 1 from the main diagonal, we'll have 1, 2, 2. I'm going to, let's see, add row 1 to row 2, 0, 0, 0. That was easy. Let's divide this by 2, 1, 2, 1, oh, and again, 0, 0, 0. So we see that our associated eigenvector, well, we're going to have 2 of them because we have two independent free variables. We'll see that our vector in terms of x2 is 2, 1, 0, and our vector in terms of x3 is negative 1, 0, 1. So we should expect our first 2 columns of P corresponding with lambda equals 1 and another lambda equals 1 to be 2, 1, 0, negative 1, 0, 1, which in fact all of our answer choices have. So we know we're going down the right road, but we still have to go through the rest of the motions with lambda equals 6. So for lambda equals 6, I will copy our matrix over. Lambda 2 equals 6. We will have -4, -3. Whoops, I can just not delete them. There we go. -3 and -3. I'm going to flip a lot of negative signs here just to make things a little easier to deal with. Okay, perfect. Let's subtract 4 row 2's from row 1. 0, -10, -5, so this row will become 2, 1. And what should we do now? Let's add 2 row 2's to row 3. 0, 10, 5, or 0, 2, 1, and we can use the first row to cancel that out completely. And as a final step, let's multiply row 1 by 3 to get 6, 3, and let's multiply row 2 by 2 to get 2, 6, 2. And then let's subtract row 1 from row 2. That will give us 0, -1, and we can change that back to a 2, 1. And dividing both of these rows by 2, 1, 1, 1/2, 1/2, we will see that the eigenvector that we get out of this is 1/2, -1/2, 1, or we can multiply everything by 2 and get 1, -1, 2. And so, finally, we have our 3 eigenvectors, and if we order them correctly, so that they correspond with their correct eigenvalues in our diagonal matrix over here, we get answer choice A. 21. 21 is A. 22, we are trying to find the eigenvalues of A. Well, that's going to be pretty easy here. Let's expand out what this determinant will be equal to. We can multiply +1 by the determinant that we get by crossing out everything else. So substituting in our negative lambda, we will have 1 minus lambda multiplied by this determinant here, which will be 2 minus lambda, 8 minus lambda, plus 5. And all of that is equal to 0. Expanding things a little bit, we have 1 minus lambda multiplied by lambda squared minus 10 lambda plus 16, plus 16 plus 5, which will give us plus 21 is equal to 0. Expanding this entire thing, I'll go up here for some extra space. We'll have lambda squared minus 10 lambda plus 21 minus lambda cubed plus 10 lambda squared minus 21 lambda plus 0, and all of this is equal to 0. Adding things up, negative lambda cubed plus 11 lambda squared minus 31 lambda plus 21 is equal to 0. And before anybody has a heart attack here, first of all, if they ever make us factor some expression like this, some polynomial of order 3, there's a good reason for it. And in this case, that good reason is that all we have to do is recognize that this 21 here means that these solutions must multiply together to be 21, because we will end up with a lambda minus our solution 1, I'll just call it S1, lambda minus S2, lambda minus S3. We know that this will factor into that form, and since our final product over here is 21, we know that the only way to get those is by multiplying our three constant terms together. And the nice thing is, the only answer choice which both solves this expression and multiplies together to positive 21 is B. So 22 is B. 23, which of the following matrices is not diagonalizable? Before anyone goes and tries like doing the actual diagonalization for all of these, I'm sure if you're using these videos correctly and you're actually doing the problem before listening or watching the solution, I'm sure some of you did, but you can actually do this problem without doing any math at all, which is pretty cool. So we know that any upper triangular or lower triangular matrix with 3 distinct values on the main diagonal is always diagonalizable. And additionally, any matrix that is symmetrical is also diagonalizable. So we have a symmetrical matrix here. It's equal to its own transpose. We have an upper triangular matrix here with 3 distinct eigenvalues, so the values on the main diagonal. We have a symmetric matrix here, as it's equal to its own transpose. We have a lower triangular matrix here with 3 distinct values on the on the main diagonal. And then right here, right off the bat, alarms should be going off in your head when you see two matching eigenvalues for an upper triangular matrix here. And since we know that all 4 of these are diagonalizable, we don't even have to go through the math, and we're already seeing big hints that A should be non-diagonalizable. But if we plug in lambda equals 0, we would like to get a matrix with 2 free variables out of it, so that the eigenspace associated with lambda equals 0 is 2-dimensional, so that in combination with the eigenvector associated with lambda equals 3, we'll have 3 eigenvectors which can altogether span R3, which is what we need to be diagonalizable. But in this case, you can just see it, if we plug in lambda equals 0, we are going to have 2 pivot positions. We'll only have 1 free variable, and thus A is non-diagonalizable. We're only going to have 2 eigenvectors. So 23 is A. 24, which statements about symmetric matrices with real entries are true? Well, what did we just say in the last example? All symmetric matrices are diagonalizable. And that, in fact, is option 4. Option 3, they often don't do this, where there's just an option in these, choose some of these expressions to pick as true questions, where there's just an option that is directly contradicting another one. So 3, there exists a symmetric matrix which is not diagonalizable. Now you might expect that there are some kind of silly exceptions to this rule, so you might be tempted to choose number 3, but I think the one that might come to your mind would be the 0 matrix like this. But just think to yourself, is this equal to its own transpose? If it is symmetric, and it is therefore diagonalizable. And obviously, it is, although it seems like a little bit of a weird case. Okay, 2. I don't know why I'm going back to front, but whatever. All the eigenvalues of each symmetric matrix are real numbers. This is also a thing, because we get real number eigenvalues for each symmetric matrix, the eigenvectors that we end up are also real valued, which leads into the fact that we get, n distinct eigenvectors for every symmetric matrix, and thus every symmetric matrix is diagonalizable. But 1 is not true. If we just go back to the 2 by 2, the 2 by 2 case of the 0 matrix that I was talking about earlier, this is symmetric. It's equal to its own transpose, but it is singular. So 2 and 4 are correct here. 24 is E. 25, consider the following linear system of differential equations. We're solving x prime equals ax. And we're looking for the general solution. We're going to do this using the eigenvalue method where we're going to end up with an xt is equal to c1, some constant. They're using b here. I have no idea why. c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2t, where these lambdas and v's are the eigenvalues of the matrix and their associated eigenvectors. So finding our eigenvalues here, we see that we'll be solving 3 minus lambda multiplied by 3 minus lambda minus 4 is equal to 0, or lambda squared minus 6 lambda plus 9 minus 4 is plus 5 is equal to 0, or lambda minus 5 lambda minus 1 is equal to 0. So lambda is equal to 5 and 1. So for lambda is equal to 5, I'll call this lambda 1. And actually, because of the way that they're ordering it, I'll call this lambda 2. For lambda 2 is equal to 5, we will be left with a matrix -2, 2, 2, -2, which we can simplify down to 1, -1, 0, 0, and our associated eigenvector, pretty clear to see, it's 1, 1. For lambda 1 is equal to 1, we will get the matrix 2, 2, 2, 2, which we can simplify to 1, 1, 0, 0, and we get an eigenvector of -1, 1. And we're ready to put everything together. So we are looking for, instead of C1, they're using B1, but B1 multiplied by this vector right here times e to the lambda 1t, which is just t. And over here, we're going to have, or I'll add the b1, b1, b2, e to the 5t. And they put the components with e into the matrices, which is a little bit annoying to look through, but yeah, C is our correct answer. That has all of the elements that we're looking for. And there we go. Okay, I don't know. See ya.